Okay, let's take a quick look at an example where we might want to use Mathematica to evaluate the limit of a function as a variable trends towards a certain value. Here's just three kind of mathy examples of how you can use the built-in limit function. Again, looking at the documentation, you can see more examples. The first limit here is a fairly straightforward limit. I mean, I don't think anybody would need to use Mathematica to figure out what the limit of x squared is as x goes to 3, but let's go ahead and execute this, okay? Notice the notation here, you get 3 squared. You've got the function that you're taking the limit of, and then you're saying, hey, let's take a variable that that function depends on, in this case x, and let's take the limit as x goes to a certain value, okay? That's a pretty obvious one. A less obvious example might be this one here. This is the limit of an expression sine of x divided by x as x goes to 0. Both the sine of x is 0, or sine of 0 is 0, and of course when x is equal to 0, it's 0. So this is a function where both the numerator and the denominator are 0 when x is equal to 0, but that does not necessarily mean mathematically the limit of this function when you take one divided by the other is going to be 0 as x goes to 0. So let's go ahead and let Mathematica evaluate it. And here you can see the limit, or what this function looks like as x approaches 0, is actually 1. And let's go ahead and just plot this function so that we can see that behavior. Okay, so here I've plotted this function sine of x over x from x equals -1 to 1. And you can see, in fact, as you approach x equals 0, so this value here, the function does go to 1. So not so obvious if you just look at the function written out, but fairly obvious if you look at the plot. Okay, so here's another example. This is x divided by 1 divided by x, and this is just an example that shows that you can also take the limit when x goes to infinity. Okay, so here, 1 over infinity, you might not be surprised that this particular function goes to 0 as x gets very large. And of course, I can also show that by plotting the function. Oops. And in this case, we'll take it from this to, we'll make it a large value. Yeah, so here, in fact, you can see as x gets very, very large, this function indeed does go to 0. Okay, so those are some math examples of taking limits, which is useful. But in physics, sometimes we ask you to take limits, or think about what happens to an expression that maybe you derived to describe some physical phenomena as one of the variables goes to 0. And oftentimes you'll find that the expression simplifies to something that maybe you solved for another system. So here's just an example from electrostatics. I stole this image here from hyperphysics. There's a link here if you want to look at that full page. But this is introduced in 183 and reintroduced in electrodynamics or electrostatics in like 381 and 382. And this is the idea that you can do an integral to calculate the z component of the electric field above a uniformly charged rod, or a line of uniform charge. Okay. Without worrying too much about how we derived this integral here basically allows us to find the full, again, z component of the electric field at a point that is a distance z above our rod. In this case, the point z is again above the rod. We're going to assume it's above the origin, and we're going to assume that the rod extends a distance a to the left of the origin and a distance b to the right of the origin here. Lambda, this character here, is describing something called the charge density, or the charge per unit length. K is just Coulomb's constant. So that's just a physical constant, okay? But in order to solve this type of problem, when you're trying to find the electric field here, you'd have to do this integral, and it's done here in hyperphysics for you, but I thought I'd show you how to do it in Mathematica. Here I've actually written out the function as it looks up here using the math palette and some hotkeys. So I'm going to go ahead and shift return and let Mathematica crunch on this. I might even skip some of the video here because I know that Mathematica is going to take a little while to evaluate this definite integral, which is why I've got this next line down here again, where I'm showing you that if you make some assumptions, Mathematica can do this integral much faster and also give you a simpler output. Okay. Okay, so Mathematica has done trying to evaluate this integral. Here you can see, like a lot of times when we try to put a physical integral into Mathematica, it's given us a complicated conditional expression that's basically saying the integral would be equal to this expression here, which if you carefully compare it, you can see it's the same as what was up here. But that's only true if this or this or this and this or this or this is true. So basically it's giving you what it thinks the answer is, but it's not sure because it doesn't know anything about z. It could be negative or positive. It could be imaginary or real. Same thing with a and b. So again, having done this a couple of times, I know that if I'm doing an integral like this, I basically need to tell Mathematica a little bit more about the problem. So here I'm saying, hey, Mathematica, before you do this integral, so I'm using assuming here, I'm going to put a list of assumptions that it needs to make, and this list is in curly brackets before I give it the expression that I want it to do the indefinite integral of, okay? So in this list, which is defined by curly brackets, there's really just two different sets of assumptions. The first one says, hey, assume that this list of variables a, b, and z are reals or real numbers. They're not imaginary numbers. The second one says, hey, assume a, b, and z are also greater than 0. Even though a is, right, this limit to the left of the origin, the way that I integrated here and the way that I put it in here, I said, hey, take the negative integral with respect to this value a. So a, I can assume is positive, okay? So these are my assumptions. Now I'm going to do the same integral. So shift return. Still going to take a little bit of time, but it doesn't take as long because it's not exploring an infinite parameter space for what that integral can be. And again, it looks a little different, but if you compare this and this, they're the same solution, okay? So it did a good job. Thank you, Mathematica. It gave me the correct expression for the integral, and now it's stored as this function ez, which is a function with respect to z. Okay, so just like it describes in this hyperphysics page, which says, note that as the limit is taken as a and b approach affinity, this approaches the infinite line charge expression. So basically, this is the expression here, simpler, assuming that this is not a finite rod or a rod with a defined length, but instead assuming that it's a rod that is infinitely long, so going infinitely long in both directions. So how can I take that limit in Mathematica? Well, I say, hey, take that expression for the finite rod, and now I'm going to let a and b go to infinity, and boom, Mathematica can easily do that limit for me. And you can see I get the same answer as Mathematica got.